Welcome to the second lecture. Thank you for coming. A special welcome because you are welcome to madness. Because this second lecture is about the interpretations of quantum theory, and there are plenty of them. Remember that in the morning we have a boring lecture just introducing the axioms of quantum mechanics, basically establishing a connection between some operations you do in the lab and the mathematical representation, and how you play with this mathematical representation to predict the probabilities of the outcomes of a specific kind of experiments. This second lecture is something else. It's about trying to explain why physicists disagree on the very meaning of quantum theory, what the problems behind this disagreement are. Because if you ask me, the main problem of quantum mechanics is that today, 100 years after its formulation, disagreement about the meaning of the theory is stronger than ever. New interpretations appear every year. None ever disappear. Remember that we are talking about what is supposed to be the most powerful and useful theory physics have ever created. So the reason of the name is that at some point in the past I had this project of trying to identify the main sources of disagreement between the different interpretations, and I started writing emails with the main defenders of some of these interpretations, trying them to agree on a minimum, and the minimum was this table. I mean, after 6 months and hundreds of emails, they just agree about this table, in which I sort of classify most or of the existing interpretations according to several things. But it was like this. I mean, I couldn't find any agreement beyond this very basic thing, so I just wrote a paper with a table and references. And then my personal conclusion was that I was making a map of madness. And why the title? If you go to the Wikipedia, you may have also similar tables with many more interpretations. And trust me, there are more. If you count, it's nearly 100 interpretations. More. Yes. So why? Why so many? And at some point I was asked to talk about interpretation. I said, how I do it? I mean, because it makes no sense. I mean, you have to explain why so many. So what I did is to try to identify the main points in which different scientists disagree and the reasons why each of them go to this direction and this direction. And after thinking, I classified the points in 3 classes. One is the so-called Heisenberg cut. I will explain. That is somehow related to the Schrödinger cut. I will explain what is that, and with Wigner's friend, I will explain what is that. So different ways to address these 3 things leads to this. Then is the measurement problem. And then is the original problem of whether there's a deeper theory behind these strange rules, which is typically called the problem of hidden variables in quantum mechanics, what at some point got something very, very interesting, which is Bell's theorem. And, well, this also forced different ways of thinking. So I will try first to introduce these concepts, and then I will try to go through the history of interpretations and how these interpretations solve or address each of these questions. The first one is kind of famous. This is Schrödinger cat. Is actually a paper Erwin Schrödinger wrote in 1935 after a famous paper we will talk about by Einstein, Podolsky, and Rosen, trying sort of make fun of quantum mechanics. Look, if you read quantum mechanics this way, you can face silly situations like this one. And this one is the following. You have a cat in a box, and inside the box, you also have a radioactive source that is emitting with probability 1/2 an atom within the next minute. And with probability 1/2, nothing happened. But if the atom is emitted, the atom is activating a hammer that is breaking a bottle that is full of poison that will kill the cat. If nothing happened, nothing activate the hammer, nothing break the bottle, nothing kill the cat. But in quantum mechanics, the decay of the atom itself is described by a quantum state as we introduced this morning. And in particular, it's a quantum state like the probability of decay or the amplitude of probability of decay is that's 1/2, and then you have the decay plus 1/√2, the state not decaying. But if you follow the implications at the end of the day, that was the point of Schrödinger, the description somebody that is using quantum mechanics is making about the whole situation from outside the box, what is supposed to be black, so you cannot see the inside, is, okay, the quantum state describing this experiment after 1 minute is this superposition. That actually means a superposition in the language of quantum mechanics, superposition of the cat being dead or alive. For Schrödinger, that was a symptom that there was something silly in the theory. But there's a more sophisticated version of kind of the same idea by Eugene Wigner, a Nobel Prize winner. He said, okay, imagine that instead of a cat inside the box, there's a friend of mine inside the box who is performing an experiment. Okay, so in the box now is a kind of source like before that can be flashing or not flashing as a source that is described from the perspective of the friend inside the box as in a superposition. But the box is closed, and Wigner, it's outside the box. Okay? And now the problem, according to Wigner, is the following, that depending on the perspective of the observer, you get a different quantum description of the same thing. For instance, from the perspective of the friend inside the box, when performing the experiment, you have two possible results. So if there's a flash, then immediately the person inside the box said, it flashes, and I think it flashes. That's one possibility, one possible outcome of the experiment. The other possibility is that it didn't flash. And therefore, he said, I noticed that it didn't flash. Okay? That's the description seen from an observer inside the box. But again, the box is black. Now is how quantum mechanics is applied from outside the box. It's applied by Wigner, which is outside the box. Well, all Wigner knows is that after a minute, the experiment has been performed, presumably, but he's not aware of the outcome of the experiment. So Wigner describes this as a quantum system that is in a superposition. So the first description is something like either this state, which is not a superposition, is state 0, or you can think about the the mind of the friend being in 0, I solve 0. That's one state, quantum state. Or the other quantum state could be I solve 1. However, the same experiment from the outside is you are, or the mind of the observer inside is in a superposition of 0 and 1. Trying to point out that depending on where you are, the theory describes, represents things in a completely different ways. The next problem is so-called the measurement problem. We introduced it this morning. This morning we said, symmetries are, reversible transformation are described by unitaries. And we put an example of that time evolution. Okay? When there's an isolated system, meaning that we prepare the system as we described this morning, but we don't measure anything, we simply leave time passing and there's nothing else, then we have a description of the quantum state, and after this time, the quantum state evolves following a unitary evolution. That's a way of evolving. Okay? But we also said this morning at the very end, there's a completely different situation. It's when we measure the system. We measure the system, and we put emphasis this morning, and there's a rule in quantum mechanics that tells you how the state transforms because of an idea, the Luther's rule, the projection postulate. And the projection postulate is simply you start with a state, and immediately you jump into a different state. And why we have two time evolutions in the same theory? This is a kind of more precise version. I think I will skip that about this unitary versus projection. But the main point is that for some very bright people, this is a clear symptom that quantum mechanics is an inconsistent theory. Roger Penrose is saying this every time. I've been saying this for years. And he got a Nobel Prize in physics. But there are more Nobel Prize winners that said exactly the same. Tony Leggett or Steven Weinberg. Okay? They think the same. They think that there is a problem because it's double evolution. Okay, next thing. Next thing is start with a paper written by Einstein, Podolsky, and Rosen in 1935. Einstein thought he had found the definite argument supporting his view that quantum mechanics is an incomplete theory. And he wrote this in this famous paper that is now referred as the EPR paper. The idea is the following. This is the version of the same argument that David Bohm wrote when he wrote a book on quantum mechanics in 1951 that is simpler to understand. Basically, they said, imagine you have in the middle a source in which you have a molecule in what we call in quantum mechanics state of spin 0 that decays into two atoms of spin 1/2. One of the atoms goes to the right, one of the atoms goes to the left. In the right, you have an observer, call it Bob. In the right, you have a different observer, call it Alice. Okay? And quantum mechanics predicts that there is a state in which, in each experiment, Alice can predict with certainty the result if Bob performs exactly the same experiment on his atom. Okay? If Bob and Alice measure, let's say, following this morning in this direction, rotate the Sturge-Lag magnet in the vertical direction, they have perfectly correlated outcomes. If one is up, the other is down. So reading my outcome, I know Bob's outcome. But Einstein and colleagues said, well, but there's a problem here because Bob can be in the moon. And there's a second problem here because what I said is valid not just for the vertical direction, but for any direction. So potentially, Alice can predict with certainty the outcome of any measurement that Bob can do in the moon. With certainty, without disturbing, because it's so far away that if we do the experiment fast enough, even light traveling at the speed of light in vacuum doesn't have time, according to standard physics, to influence the outcome or to change the outcome. But there is a problem, they said. According to quantum mechanics, no system can have simultaneously well-defined values for two of these quantities. Therefore, they conclude, this means that quantum mechanics is an incomplete theory. That's 1935. At that time, quantum mechanics was so successful that basically few people pay attention to Einstein and to this. Only in 1964, a physicist called John Bell took the idea seriously, in the sense that he really go to the details and imagine a theory like the one that would please Einstein behind the explanation, behind quantum mechanics. But he makes a small change in the experiment, in the original experiment. Because now, Alice can measure two things, represented by these two bottoms in the left box, with two possible outcomes, and Bob two things, but they are not the same things. There are slightly different things in the left-hand side and in the right-hand side. Okay? And now he defined this quantity that is the mean value of the products of the outcomes. The outcomes can be called +1 or -1. So in each round of the experiment, one of them get +1, the other get -1. And when they repeat the experiment a million times, they go together, said, okay, in this round you get +1, I get -1, therefore the mean value was -1. In the next round, you get -1, -1, so the mean value was +1, and so on. We do, then we divide by the million, and then we have each of these quantities down for each of the four possible combinations of what is measuring and what is the measuring. And John Bell realized that in any theory like Einstein would like, this quantity has an upper bound. It's 2, cannot be larger than 2. However, according to quantum mechanics, you can prepare pairs of particles in a quantum state, and you can find local measurements represented by these self-adjoint operators we mentioned this morning, that when you apply the Born rule we explained this morning, you do all the calculations, you get 2 square root of 2, which is 2.83. The S less equal 2 is what we call nowadays a Bell inequality. And the prediction of quantum mechanics, namely that there's a violation, and this violation goes up to 2 square root of 2, has been tested. To the point that in 2022, John Clauser, Alena Specht, and Anton Zeilinger got the Nobel Prize in Physics for the experiment testing this prediction of quantum mechanics. So it's a well-established prediction. So any interpretation, any view of quantum mechanics has to explain everything we said so far. Has to answer what is going on. But let's start with the, let's say, by default interpretation, the favorite interpretation among physicists. namely the so-called Copenhagen interpretation. Actually, everything is wrong. There's no such a thing. I have to be honest. In Copenhagen, starting in 1926 or 25, Niels Bohr created an institute and called Heisenberg, Pauli, to discuss all these things. And they were discussing every day, any minute of the day, and most minutes of the night as well. And they have a strong disagreements. But they were trying to say what's going on, together with Max Born as well, which are all the characters you have here. But in some of this, in many of the, and actually many of the discussions, they have different opinions. Some of them really, really different. But at some point in the 50s, Werner Heisenberg coined the term Copenhagen interpretation, sort of hand-waving, assuming that there was an agreement on what they think about that. What is partially true, but just partially. And this is what we call nowadays the Copenhagen interpretation. What is that? First of all, one surprising thing is that although the theory was kind of invented or found or in 1925 in July, basically, already next year, in matter of months, they already write things like this. Quantum mechanics is a closed theory whose fundamental physical and mathematical assumptions are no longer susceptible of any modification. That was a surprising statement, but they were right. They were right. And then he said, a quantum prediction, this is particularly Niels Bohr insisted on that, a quantum prediction, and therefore the ascription of a quantum state or a wave function requires you to completely specify the whole experiment you are talking about. Niels Bohr was constantly emphasizing this. You need to specify the whole thing, otherwise the theory makes no sense. Then they reached the conclusion that the values you get in the experiments, the +1, the -1 we mentioned before, cannot be attributed to an observable, to something, to property that existed before you measure. Okay? Even when you, in the case of Einstein, you can predict with certainty that if in the moon Bob is going to measure this, I'm pretty sure that it's going to get +1. This is not enough to attribute that there's a property in the moon that forces this particular outcome. Okay? The main thing they defend is that the result of a measurement of any of this experiment is intrinsically indeterministic. And moreover, this outcome, by design, is irreversible. It's a process that involves irreversibility. Moreover, the wave function, the quantum state, is only a catalog of outcome probabilities relative to a set of possible measurements. It's not a field. It's not a wave. It's not a cloud. It's just a catalog. It's a mathematical, to be more precise, it's a mathematical object that hides a catalog of probabilities when you combine with the mathematical object you use to represent the possible observable. Nothing else. There's no measurement problem. Here overreading Copenhagen, I'm adopting, let's say, a much more modern perspective. Actually, this is taken from a statement by David Mermin, but it's like, if the entire content of quantum state is a catalog of probabilities it gives rise to, then each user of the theory is acting as a statistician. The acquisition of further information by the scientists can lead to an abrupt change in those probabilities and thus to and updating of this catalog, namely the quantum state. So the fact that there's an abrupt jump in a measurement between the quantum state before the measurement and the quantum state after the measurement is not a problem at all. The so-called collapse, meaning this jump is the name they start to use, the collapse, that you start with a particular state, it collapses into a new one. The collapse of the quantum state is only a change in the information available to the observer. Because the quantum state is just a predictive tool. And then, thinking about Bigner's friend, a particular observer, the friend inside the box, may have better information, more complete information than another particular observer, namely Wigner out of the box. Okay? And then, they strongly disagree on a fundamental point, which is the so-called the cut, the Heisenberg cut, because they agree that there's a fundamental division between the system being observed and the device you use to measure that system. And this is called the Heisenberg cut. And they insist that the measurement device might be described in the language of classical physics. Okay? And the cut, the Heisenberg cut, is this boundary between these two things, the observed system versus the classical measuring device. And then if you ask Heisenberg, where is exactly the cut? Heisenberg would say, it's flexible, it's a mental construction. You can put the cut, think about the Schrödinger cat, right? It's in the box, you can put the cat in the box, you can put the cat in the poison, you can put the cat in the hammer, you can put the cat after the decay. It's flexible, it's a mental thing. That's why you have the description. But Niels Bohr strongly disagreed with that. Niels Bohr would say, no, that's not true. In this experiment, the cat is there. I don't want to anticipate where Niels Bohr would put the cat in the Schrödinger cat experiment, but there was really a clear disagreement between Heisenberg and Niels Bohr about that. You can read about that in this reference. But then there's the famous sentence that everybody used. But actually, the origin of the sentence is not what people said. This is a sentence people attribute to Richard Feynman. Richard Feynman never said this. Okay? Never. Check these references. This is in a paper written by David Mermin in '89. And the context is exactly this. If I were forced to sum up in one sentence what the Copenhagen interpretation says to me, it would be, shut up and calculate. But according to the survey conducted by Nature that I mentioned in the previous talk, most of our colleagues, physicists, subscribe the Copenhagen interpretation. Most means a majority of them. But it's a small majority. It's 36. And now look about how many of them are really confident about that. Less than 7%. Actually, the most interesting thing after that observation that the majority of the physicists prefer this Copenhagen interpretation, whatever it means, is the last row. If you really look for the most confident ones, are really ones that are really not subscribing any of the standard interpretations, which is also interesting to note. But this is, let's say, the by default. And then, what is the problem? Well, I don't say it is a problem, but I have some questions about those who are proudly defenders of the Copenhagen interpretation. Is that what qualifies as a measuring device? What do you need to really make an experiment like this? Why we cannot use a bottle of wine as a measuring device, or why we need this strange magnet followed by screens? Why? Can you give me a recipe too? What is really a measurement and what is not? Because there are zillions of interactions in nature. Why some of them qualified as measurements that you describe using quantum mechanics, while others don't? Where is exactly the cut between the measure system and the device? And together is what qualifies as a quantum system? Why you need, remember how we define a quantum system this morning. You need to not just tell me how you prepare the physical systems, you have also to tell me what are your plans for measuring on them. Then, and only then, you have a quantum system. But you have to give me why the bottle of wine together with a fork knocking the wine is not a quantum system, or maybe is a quantum system. I don't know, but I want you to give me some details. These more or less are standard questions about Copenhagen, but then I have my favorite question. But actually, I will ask this question everywhere. Why quantum mechanics works? What property of nature, I'm still saying nature, produces phenomena that cannot be explained with classical physics and can be properly reproduced using quantum mechanics? Because the interpretation in this sense is really saying what David Mermin said, shut up and calculate. Good, this is the standard thing. Let's move on. In 1927, Louis de Broglie, in a famous conference in Solvay, organized by Solvay in Brussels, together with Einstein, Bohr, Heisenberg, Pauli, Dirac, Schrödinger, Marie Curie, many people, came saying, I have a better interpretation of quantum mechanics. To be polite, Wolfgang and Pauli killed Louis de Broglie that very day. But exactly the same interpretation was rediscovered by David Bohm in 1952. And it's kind of interesting because David Bohm wrote a textbook on quantum mechanics, very nice one. But the moment he finished the textbook, said, I don't buy it. He found out his own interpretation, but is exactly or essentially equivalent to the Broglie interpretation. That's why I call it the de Broglie-Bohm interpretation. Also known as pilot wave theory, also known as Bohmian mechanics. Each particle in this interpretation has a position, is a ball, is a marble, has a position and a velocity. Super attractive. The evolution of this particle is guided by, depending on the language, a guiding equation in the pilot wave or a quantum potential that is decided where to go. It's fully deterministic. But it's explicitly non-local, in the sense that if Alice decides to, Alice is, okay, I'm measuring this direction, oh no, let's measure this way. This instantaneously change the quantum potential all over the universe. Not just the moon, all over the universe. Instantaneously, whatever it means. And not only that, immediately that was David Bohm realized that you also need something else. Because the Born rule is not a basic law in Bohmian mechanics. you need an additional assumption that basically you need to assume that at the beginning of the universe, the hidden variables had a particular shape, because otherwise you cannot explain why the Born rule works. So he wrote a paper in 1953 saying that, and has the name, this quantum equilibrium hypothesis. Okay? I have many questions for Bamians. I try to be brief. Here is what dictated the initial conditions of the universe. Well, maybe that's not scientific questions. And that's my favorite questions. Is there a consistent relativistic version? Because we know relativity works. We have a symmetry that is Lorentz invariance. Everything, every theory that works has this symmetry, but it's impossible to have a Lorentz invariant version of this Bohmian mechanics, precisely because everything changes instantaneously everywhere. And people have been working for this for years without really getting any convincing solution. And then recently, people have rediscovered an old problem. Let's look at picture the whole thing, using the simplest atom in the simplest state. Hydrogen is just essentially a proton and an electron. The good thing about Bohmian mechanics is that it provides a picture of what is happening. You have really particles. Okay? So, if you really go and solve the equations and everything for the fundamental state of the hydrogen, what is the picture? The picture is you have a ball and you have a ball. Keep looking, because it's not going to change. It's like this. This is the picture. Two balls static in the air. That's the picture. And has been forever like this, and nobody pay attention. But recently, about a month ago, there's a paper in Nature in which people realized that, well, one thing is the Bohmian particle. We tend to believe that the Bohmian particle is the electron. But what about other situations? So they do an experiment in which Bohmian mechanics makes specific predictions about the speed of the Bohmian particle in an experiment that we typically said they are photons. But now we can measure the speed of photons. So this is what they did. They measured the speed of photons, they compare with the speed of a Bohmian particle. Totally different things. That's the recent news about Bohmian mechanics. And then we have the many worlds interpretation that once more was kind of discovered, rediscovered, and so on. Hugh Everett was the first one, 1951, and then was Bruce DeWitt, and then many other people, and then these days David Deutsch is like the great pope of many worlds. There's a single universal wave function that follows a unitary evolution. It's fully deterministic, but in each measurement, the world branches, divided into as many branches as possible outcomes the measurement has. And each observer just see one world. So there are many worlds, but we all always in the same world. But there's a technical problem nobody mentioned, that again, as in Bohmian mechanics, Born rule is not guaranteed. So here is like, they make a calculation that said, in the majority of the branches, observers will observe Born rule. But there's many branches in which Born rule doesn't hold. I found it interesting that when you ask David Deutsch why you are subscribing this, at the end of the day, it's simply because he said, I look around, I see all the alternatives, and all of them are nonsense. So I keep this one. Many questions to Everettians. What dictated the initial conditions? Notice that they are just saying, okay, there are two evolutions in, let's say, standard quantum mechanics. So they are saying, well, actually, no. There's one evolution. It's unitary evolution. Okay? The other is an artifact. So they address the double evolution by selecting one of the evolution as the one. But where is the physical motivation of the branching between walls besides solving a mathematical problem? So it works in solving that, but what is the physical justification of the branching? Why the universe are branching? What are the physical principles behind the whole thing? And then my obvious question, everybody's obvious question, aren't so many walls a brutal ontological cost to describe this problem, I mean, to solve this problem? And the practical question is, well, in the last 25 years, we've been doing we tested, the Born rule is still there, it's still working. I mean, we've been constantly in the same branch of the universe. So because, okay. Eventually, at some point, I would expect to see a violation of Born's rule, but we don't. This is the other alternative. There are two evolutions. You can assume that the right evolution is unitary, as in in many worlds. But the other alternative is, look, the unitary evolution is just approximate. It works for microscopic systems, but there's some moment related to the mass of the system or the complexity of the system in which this doesn't hold anymore. That's the basic idea behind a model proposed by Giancarlo Girardi, Alberto Rimini, and Tullio Weber. But then the Schrödinger equation, which is what is effectively implementing this unitary evolution, is supplemented with additional terms, nonlinear terms, stochastic terms, they call spontaneous collapses, with localized, which makes the wave function, the quantum state, to collapse to become one particular state. This set of theories that are called spontaneous collapse models have an amazing virtue, namely you can test them. You give me the model, in principle, typically there are predictions that are slightly different than the corresponding predictions in quantum mechanics. This is what many famous people are advocating, including Steven Weinberg, Roger Penrose, and Tony Leggett. I have a question for them. Why after 100 experiments there's no evidence of that? Again, you are once more creating these extra terms and so on to address this double evolution. Now it's not unitary, it's the other way. Do you have any physical reason for doing that besides solving the mathematical problem? You have principles behind it, and again, famous question, why quantum mechanics works? And how you solve non-locality. And the only way to solve non-locality in collapse models is by believing in spooky actions at a distance, instantaneous actions, using the name Einstein used. Then we have something else, which is retrocausality. The funny thing is that it happened many, many times since history. I mean, the first one who proposed a solution like this is Satoshi Watanabe. Then Yakira Haronov recovered that. Then Brans. Then many people have played this game. And depending on who, this is slightly different, but it's like this. The information about the future measurement settings, when we're doing an experiment, the information about what is going to be the setting of bulb is made available to the measure system when the preparation, so they know the future somehow. There's a mechanism that allows them to know the future and knows what you are going to measure. Maybe you don't know, but they know. Okay? Then this forces the particles to be prepared one of the eigenstates of the future measurement settings. Okay? Each particle is described in the model. Now I'm talking about Brahms in an ontic quantum state. The preparation determined quantum state is an epistemic quantum state. But both the ontic and the epistemic quantum state evolve according to Schrödinger equation. Each particle has a definite position at all times with a velocity given by something that mathematically resembles a lot the Broglie-Bohm type guidance equation. The trajectory of the particle and the measurement outcome is determined locally by the ontic quantum states. There are plenty of versions of this in which you have states from the past, states from the future that meet exactly at the time of the measurement. And they conspire to this. These are retrocausal models. Questions: what dictates the initial final conditions when? Is a relativistic version of this. And main problem, retrocausality challenges our intuition of time and especially lead us to wonder why we don't see more evidence of the future influence the now. We said evidence of the past influencing the present, but not the future influencing the now, at least in my case. What are the physical principles? And then we have, for instance, relational quantum mechanics proposed by Carlo Rovelli. Every physical system is a quantum system. Notice the contrast with what I said this morning. A quantum system is operationally a completely different notion than the notion of a physical system. It would be nice, it would be simpler if this is the case. Every physical system is a quantum system, and every quantum system can serve as an observer or a measuring device or both. There is no fundamental division. A measurement is simply a physical interaction between two systems. The outcome of a measurement is created during this interaction. The collapse is not a physical process affecting the whole universe, but it's an update of the information that one of the system has about the other system following the interaction. The collapse is relative to the system. The complete description of the wall is given by the set of all relative states. Reality is not a collection of objects with intrinsic properties. Reality is a network of relationships. I tell Carlo that he is one of my favorite poets. And it is. I mean, he writes beautifully. I typically add, he writes beautifully even when he's wrong. But I don't want to contaminate you. I just have a question for Carlo, is that if a tree is fundamentally quantum, please, Carlo, describe, at least at a Gedanke level, imaginary experiment, an interaction that I can make on a tree that allow us to prepare any quantum state and implement measurement, any quantum observable in the corresponding Hilbert space. Because I want to do that experiment. I'm super curious on that. Please give me a Gedanken. Now, it may take 1,000 years that we can really make the experiment, but I would like to have a recipe now. Why quantum mechanics works. This is beautiful, this poetry, but it doesn't explain why it works. What property of nature produces phenomena that cannot be explained with classical physics but is accurately predicted by quantum theory. And then we have cubism. The main proposer of cubism is Chris Fuchs. And I put 2010 today because he recognized that this is an unfinished project, it's still in the making. According to cubism, the quantum state represents the degrees of belief a particular agent has about the possible outcomes of measurements. A quantum state is personal and is about own belief. The Born rule is a normative empirical addition to good decision making. Cubists want to reconstruct quantum mechanics from basic principles. Their goal is to identify what aspect of the ontology of the physical world make quantum mechanics a good tool for agents to use. So they recognize that there is an ontology there. Okay? So, but they really see quantum mechanics as a tool. Then they have a technical issue that we like to discuss with him, that they privilege a particular kind of measurements, seek POBMs, blah, 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 but I will skip to that, and they have the reasons for that, but it's not important. And then the questions, these are real questions in emails to him. So I said, I don't like these SIG POBMs because they are ugly as foundational tools, but my main question always is this: imagine that Wigner's friend, I understand that Wigner's friend is the main motivation behind cubism. Okay? If you take it seriously, this enforces the quantum state that Wigner assigned to be understood as a personal to Wigner. But imagine for a moment, I ask Chris Fuchs, that Wigner friend, in the case of Wigner friend, Wigner, as Bohr would defend, cannot legitimate use quantum mechanics simply because it doesn't have full experimental details. Okay? Then, rather than personal to Wigner, the quantum state would be something like relative to the missing experimental details, and the outcomes would be objective rather than personal. Wouldn't they? But at the end, same question. Even if you think this is a kind of safe way. Actually, if you really take seriously the exercise we played this morning, that let's separate quantum mechanics into a probability theory and the physical implementations. Forget about the physical implementations, and you really believe that this probability theory is that probability theory, and everything that you can imagine through this probability theory happens in the lab, no matter how you, no matter how the ingredients, no matter how the experiment. Then, in a sense, cubism is logically enforced. But again, it doesn't, even in that case, even from that perspective, it doesn't answer why the whole thing works. In particular, why Born rule? Why is an addition, an empirical addition? You use Born rule because experiments suggest that it's the right way to compute probabilities, but why? And then we have superdeterminism. And the main defender of superdeterminism is Gerd Tauf, who got a Nobel Prize in Physics in 1999. Gerd Tauf has many interesting points. He said, quantum mechanics only describes the average and never goes beyond the average. Underlying quantum mechanics is a world obeying totally classical laws. Superposition is a mental construct, whereas the real world doesn't really have that. We created the problem by our choice of this convenient tool of quantum mechanics to do our statistics for us. For example, he said, in reality, the vacuum, what we call vacuum, is probably a very complex fluctuating mode. If you make superpositions, you can make a single state look like the vacuum. Physicists are never able to conduct a fully controlled experiment because the experimental setup they choose is not independent of the process that created the systems they measure. Free will is an illusion. We are sort of assuming that Bob is freely choosing between measuring this and that. Gertov is saying, no way. This is somehow determined by the Big Bang. There's no free will. The universe is not just set up in advance. It is set up in advance to fool you. This is real, I take this. And it's set up in advance, presumably because the entire universe started with a single Big Bang. So it's where everything started. So questions or criticism. This is a direct threat to science. Superdeterminism undermines the scientific method. If we cannot assume even that our experimental settings are independent of the system we study, then experimentation and testing theories makes no sense. And technically, it has a fine-tuning problem. What Toph is describing is a huge conspiracy, huge. It's a conspiracy to ensure that the hidden variables that we don't see are exactly correlated as to satisfy all predictions of quantum mechanics. Exactly tuned to that, no more, no less. It is exactly tuned to fool us, to make us believe something else. And then, this is all, probably some of you have heard about all this interpretation, but starting in 2000, there's really a very, very interesting, productive, fruitful, deep attack to the problem. It started with this paper by Lucian Hardy, which is trying to reconstruct the axioms of quantum mechanics as I presented before, mathematical axioms that corresponds to operational actions in the lab, from a set of principles. And he proposed the first set of principles, looks like this. If you put together, I will be very, very fast here, causality, local discriminability, perfect discriminability, ideal compression, atomicity of composition, and purification. You mix this, you get the Hilbert space formalism. Problems. People said these principles are ad hoc. They are not fundamental. They are not physical. They are not operational, as the author said. On the contrary, the principles are carefully chosen because the authors already know that they lead to quantum theory. In any case, and this is admitted by their own proponents, the sets of principles themselves still lack of true explanatory power. They just show that certain principles, sets of principles, are logically equivalent to the quantum formalism. But this, if you ask me, is really important. This is a really improvement in the development of this problem. But it's true, the principles they choose, they don't never explain why the universe apparently chooses these specific principles holding the universe or in our description of the universe. And then I would say that another problem is that if we would have just one reconstruction like this, like Hardy, the first one, that would be nice, but now we have 13, and they are slightly different. And this, there are too many different sets of axioms. Which one is the right one and why? But all of them kind of suffer from similar problems. And there are more technical problems about they fail to describe infinite dimensional quantum mechanics as well. And as Lucy and Hardy confess, they fail to solve the interpretational problems. For instance, Lucy and Hardy frequently said, when I started this project, I have this dream of once I have in front of me the axioms, I would understand what is the right interpretation. But it's not the case. Good. So, I can keep talking and talking and talking. I said there are 50-something interpretations like this. But what is the problem of quantum mechanics? That nobody has a solution that convinces everyone, that no interpretation or reconstruction explains, I added at the very last time, in a convincing way, because Bohmian mechanics explains, everything is written in the first quantum potential, where quantum mechanics come from. We have been like this for 100 years. And now the question, and this is the question for the next lecture, is how to solve this problem. So the next lecture is an attempt to solve this problem, to understand, to identify where does quantum theory come from, what is this property of nature that makes this Hilbert space formalism so successful in making accurate predictions. And for that, the plan is identify what I think is the most distinctive signature of quantum theory as a mathematical theory, and try to explain just this signature in the sense of how a universe should be to produce a signature like this, such that I program a toy universe, I put this principle, this signature, I play, and then I generate a universe in which scientists are enforced to use quantum mechanics if they want to make optimal predictions. And that's the plan for the next lecture. Thank you for coming. Questions?
Thank you. Yeah. Locality. All the interpretations. Okay, sorry. I repeat the question. All the interpretations include locality, or is there an interpretation that is local? The other one, how the relationship between relativity and non-locality is addressed?
Okay, good. Okay, non-locality actually is the proper way of saying is that there's no local hidden variable explanation of the predictions of quantum mechanics. And what local hidden variable means is 4 things together. First, there are hidden variables. There are things we don't know that are traveling in the particles that are separating. Okay. Second, there's an assumption that is fundamental, is that the measurements we do in these non-locality experiments are not related to these things that are troubling. They are independent. This is a basic assumption. Third, once the measurement is set in this site, we also assume that this measurement or this choice is not transmitted, is not known, is not affecting the outcome in the distant particle. And fourth and last, once we have the outcome, we assume that this outcome is not communicating instantaneously to the other outcomes. So we are assuming when we say local hidden variable theories, is we assuming all these four things. How the different interpretations address that. Bohmian mechanics is explicitly failing at least the communication part, because in Bohmian mechanics, the moment Alice set the setting here, this immediately propagates to the rest of the universe, so affects the outcome. So Bohmian mechanics fails to satisfy what is called parameter independence, which is the third assumption. Collapse models have to fail somehow to satisfy parameter independence. Superdeterminism failed to satisfy measurement independence, which is the second assumption. There's no free will. You think you choose yourself, but it's actually everything is decided in the Big Bang. The same for retrocausal models, but the decision is also somehow in the future. Cubism, relational, Copenhagen escaped from non-locality, saying there's nothing non-local. The state is just a catalog. You are just updating things. So there's no, it's a tool. There's nothing you cannot use. In any case, we know that we cannot use the predictions of quantum mechanics to transmit information at superluminal speed. That's a fact. And you can prove that. But they said they go more. I mean, all this non-locality in the sense of spooky actions at a distance is due to the fact that you try to attribute an ontology to the very wave function. You said it's not just a mechanism, it's kind of real. When I can predict with certainty, it's because there's something there, okay? Even if I don't measure. While cubism, no, you do. It's just a catalog of probabilities. It's a way of betting that managed to work optimally. That was the first question. What the second question was about?
The relationship, how...
relativity.
With relativity.
Okay, relativity is a big issue. It's a big issue in Bohmian mechanics. You have this deterministic version, but there's no way to make it compatible with relativity at the level of the hidden variables. There's no way. There's no need, there's no problem, there's no tension in Copenhagen, cubism, and relational, simply because they use this as a tool. Relativity is also a problem in collapse models. Relativity is a super problem in retrocausal models. But it's probably not a problem in this, well, it is a problem in superdeterminism, but since universes conspire to that. What else we have in the catalog? There is no problem. I mean, many worlds escape from relativity also by this abundance of ontology and the fact that by law there's no communication between the branches. And I think as far as so, yeah.
I wanted to address.
Very close.
Sí. About free will, and now we're getting more maybe metaphysical. So, well, I quoted David Bohm, since you talked a lot about him, and it says, consciousness exists as a field of information stored in quantum form throughout the universe. So what do you think about that?
David Bohm was consistent in his writing and his books on this model I mentioned in 1952. So the Bohmian universe is a holistic universe. Every single thing we do is automatically affecting every single point of the universe. Yeah, that's a mathematical fact. And it's never clear to me, probably, is whether you have free will in the Bohmian universe, in the sense that everything is determined, most likely it's also determined. So it all depends on how you applied Bohmian mechanics. You can apply Bohmian mechanics under the assumption that you have free will to decide, and then you have the problem of how this influence instantly. Or you can say, well, if everything is deterministic, why not we are all in the quantum potential, and at the end is not very different than superdeterminism, in addition being holistic and so on. But the issue of free will is important. It's connected to the Bell's theorem of the previous question, because the basic assumption in Bell's theorem is measurement independence, which is violated by superdeterminism, is violated by retrocausal models. You can also prove that measurement independence is strongly connected to parameter independence, which is violated in Bohmian mechanics. And technically it just means that the hidden variables, this deeper description, the assumption is that it is decoupled to the decision of the measurements. Okay? We typically call this free will because we think that we do have free will to choose the measurements. But just from the practical side, in reality, there are few experiments in which we take the decisions. We actually ask a machine to take the decisions because there are many decisions to take. So it might make sense to think that there's something in the universe influencing the hidden variables. So far, so good. But we recently discovered the following. If you allow the hidden variables to influence, to determine absolutely everything, there's no way out. They do everything. But imagine for a moment you said, okay, this influence exists, but like the influence when you pick up the menu, you said there's a menu and you know your own disgusting dishes and there's 3 or 4. So in a sense, you don't really use the free will. There's some correlation between your final decision and previous hidden variables. So what I'm trying to say is that imagine that, let's say, 90% of the decisions in these experiments are really governed by the hidden variables. But just 10% are not. Well, we recently discovered that quantum mechanics also makes a prediction about that, in which you cannot reproduce quantum mechanics even under this assumption of partial lack of free will. And the same applies to superluminal communication. Imagine you said, oh, there's superluminal communication, it's a kind of fluctuation of the universe that happens that there's superluminal communication 50% of the times, or 60 or 70, but the rest doesn't work. Well, we recently discovered that, at least theoretically, even if it's 90% of the times in which you have superluminal communication, but if you have just 10% in which there's no superluminal communication, again, there's a prediction of quantum mechanics that cannot be explained, even with these spooky actions at a distance that Einstein hated. To be clear, just in the case that the spooky actions at a distance just play 99% of the times. If they play the 100%, yes. But if just play 99%, is not enough to really reproduce quantum mechanics. So what I'm trying to say is even this whole discussion is really changing these days. We are conducting experiments trying to check these predictions of quantum mechanics. And so there are new things to add to this discussion.
Adán, could you explain the difference between interaction and measurement?
Yes. The measurement, what we mentioned as measurement, I tried to do this in the morning. A measurement is an interaction between a physical system and a bunch of physical systems that produce, in addition to releasing the physical system, produce a click, a spot, something you can copy. You may have an interaction in which you do something on the physical system, but you don't have any click, any outcome, any trace of that interaction. A measurement is a particular interaction in which, by design, you want to have a trace. A trace you can play with in the sense we played this morning. You can correlate the number of times you get this outcome. For this particular box, I have 80% this outcome, 20% this outcome. Then I classify it. But I need a mechanism here that not only interacts with the physical system, but also gives me a number. In the case of the Stergelach experiment I mentioned this morning, you have a silver atom. I will do this, but this is totally forbidden. It's against the spirit of this talk. It's a silver atom moving in the magnet, and there's a screen. There's nothing like this. Well, the magnet is there, but there's an oven emitting with a hole with silver atoms, and at the end, there's a screen, and the silver atom, actually a bunch of silver atoms are up, another bunch are down. Okay? And this is, okay, up is +1, down is -1. So this is the click. Then I can copy, said, I have an intensity, I have 80% up, 20% down. I can give this. In a more sophisticated experiment, in addition to do that, you get exactly the same clicks, the same probabilities, and also you can keep performing measurements. So you have a trap ion, you perform a measurement, you have a click between these two, you record a click, then on the same ion, you perform a second measurement, you record the outcome. And you can, in principle, you can keep going and going and going. And this morning when I mentioned the dream experiment in quantum mechanics is one in which you can do that. And actually we can do that. You prepare, you perform a measurement, you get a click, and anticipating the next lecture, you can actually do a measurement so good that you repeat the measurement and you get the same outcome. And you repeat the measurement, you get the same outcome. Like in usual measurements. Right? So there's a difference between interactions, general interactions. Moreover, it's more precise that this outcome, this click, should belong to a specific set. So you should anticipate how many possibilities are. There are 2 possibilities, up and down, no more. Or 3 possibilities. So a measurement is a very, very specific interaction with a lot of conditions. You need first this irreversible thing that produces a click. The click should belong to a specific set. We said this morning, this specific set should be, you can put in correspondence with a number, with the real numbers. So it could be infinite sets, but you should know in advance. You have to define that and then said, okay, this is a measurement, at least in these experiments we're talking. And your question is going to be very important tomorrow. Okay, measurements are very specific kind of interactions in which we demand a lot of things to a measurement. So when we said a measurement, we have to enforce a lot of situations. I mean, it's typically neglected when we explain things like the Sturgelag experiment, the difficulty of the experiment, the fact that they choose basically any other atom, you can't get the effect. It's a very precise combination of ingredients and the way these ingredients are combined. While interactions, there are many interactions that don't satisfy these requirements. It's a very good question. I'm really happy to go that direction, but this is the fun day. This is more for tomorrow in the sense this is the crazy madness thing. Your question is really deep. It's going to be important for understanding what's going on. Okay. We put examples of measurements, even in classical measurements. And this is.
Not a scientific question. What is your preferred interpretation?
When in 1991, I was fascinated by David Bohm. I mean, because he was an outsider, but actually he was providing really a picture. Everybody wants a picture, and this guy, an outsider in the field, and he was expelled from the United States because he was kind of communist and had a very troubled life. And to me, he was a kind of hero because he was really given the solution. And so I was attracted by that. But then immediately I started doing calculations, and then I noticed that, I mean, when I saw the electron, well, the Bohmian particle in the hydrogen standing still at the top, I said, this makes no sense. Keep going. Then I started to believe that I was a Copenhagenist. I said, there's no problem. I mean, like Matthias, there's no problem. If you read this, there's no problem. You can sleep properly, and there's absolutely no problem. For years, it was like this. Then Cubism enters into the business, and I spent basically 7 years asking myself whether I was Cubist or not. Really, just to. And then somebody asked me about a talk on interpretations, and then I had this exercise I made today about understanding why people have all these different visions. And then I realized, and this is my final answer, the none of interpretation is enough, is what I try to say. Even if you are Copenhagenist, what is your answer to when is a measurement? What is needed? Why the Born rule? Why it works? What is going on? I will start with that. Is fundamental indeterminism. No, come on. That's good when you're a kid, but you cannot derive from fundamental indeterminism the Born rule. You cannot derive the Hilbert space. I prove that you cannot. So no one did. That's why I particularly was, besides interpretation, so my answer is none, a big none, but I was really attracted and I learned a lot from the works of Lucien Hardy, Giulio Chirivella, and colleagues, Massanes and Müller, Bruckner and Dakik, name it. I mean, they really try to say, you can throw away. They did something very nice. You can throw away all the axioms in this dry way I presented this morning intentionally, and replace this dry set of axioms, establishing purely connections between some operations and some mathematics, by something else. If you imagine a theory in which the observers will have this ability and this and this and this and this and this, then you have quantum theory, more or less. That was super nice because it was a completely change with respect to the previous years. But then the other day somebody asked, what was the final thing, what was the final conclusion of this reconstruction program? And the final conclusion is what I tried to summarize in the slide is, immediately people said, this axiom, come on, this is ad hoc. This is exactly what you need to finish the puzzle. But you don't have any physical reason why. You know that if you put it, you have it. Or this axiom, or this axiom. And then people start discussing different sets and saying, well, this is basically the same thing. But then Lucian Hardy started, at some point Lucian himself said, I was very excited at the beginning, but this is it. I didn't really answer my own questions by my own approach. What I'm trying to say here is that if you ask me what is the most valuable contribution to all this discussion we are having, is precisely this reconstructions program. And what I will try tomorrow is in that line. But I won't offer you, local tomography, purification, and I will try to convince you that every single step I take is the step John will take in the very same situation. So it's the way to go. So that's my answer, none.
Okay then. Thank you very much for this second lecture. Tomorrow we have 2 more sessions, but not here at the Faculty of Arts, remember, but at Montilivi, at campus Montilivi. So thank you very much. Since we were into madness, we thought that would be a good idea to have a drink.
That's perfect. That's perfect.
Right. So, but at a macro level.
It's perfect. Let me finish with a joke that Arthur Ecker made. He said, if you put together in a room a group of human beings and you force them to talk about interpretations of quantum mechanics with bottles of wine, at the end of the experiment, you will have more interpretation than human beings.